Hello and good morning. My name is Allan James. I'm the Managing Director of Semefab Limited, a company which I founded 34 years ago. Semefab is a manufacturer of semiconductor and sensor devices. We turn silicon wafers, such as this, into semiconductor devices, power switching semiconductors and sensors, which are integrated onto printed circuit boards. Here's an example, and they end up in products you'll be familiar with, such as CCTV cameras, cars, medical instrumentation, consumer and white goods. Come on, let's go inside and I'll show you around. This fab is the original fab, the Fab 1. It's a 34-year-old fab, so you'll see some distinct differences in the design and the equipment of this facility compared to Fab 3. But nevertheless, it's still quite a good working fab. It produces excellent quality product. Let's go in. So here we are in the Fab 1 furnace area. In this area, we subject the wafers to high temperatures in oxygen and hydrogen environments to create silicon dioxide, or with phosphorus or boron to drive in impurities into the surface of the silicon. This is an example of a furnace tube here. We've got several of them. You can see the wafers are loaded on cantilevers. They're supported so that they don't scratch as they go in and out of the furnace, and they don't create any particulate. So we're coming through now to the pre-diffusion clean area and through to the etch area. After the wafers have been through the clean, they need to be rinsed to take all the acid off. That's what these weirs are for here. You can see there's a flow system. There's a first rinse weir and a second rinse weir. This is the 18 megohm water that we saw or you'll see in the facilities area when we show that. Once they're rinsed up to 18 megohm centimeter, we then put them into the spin rinse dryer here, these semi-tools, where they're literally spun just like a washing machine and dried. So there are two ways of etching, wet chemistry and what we call plasma etching, which is dry etching, and Semefab does both of those. So this is our dry etch area in Fab 1, and here we have a variety of tools that can etch wafers in what we call a plasma. A plasma is a bit like the gaseous discharge that you have in a fluorescent light tube. So when we strike plasmas in these machines, actually you are creating light, but you're also creating an aggressive mix of the gas species that is able to etch the silicon. And the gas species are volatile, so they disappear in the pumping system. This is the LAM 500. This is used for oxide and polysilicon etching. The TGAL system, TGAL 903, this will etch silicon dioxide. You can see this is a cassette-to-cassette system. This tool here is a matrix stripper. So with every photolithography step, at some point after you've done the etching or the ion implantation, we need to remove the photoresist. The photoresist is just a means to create a pattern on the wafer. This tool is the Electrotech 4200. It's a plasma, it's a sputter tool for deposition of metal, and we're typically depositing here aluminium 1% silicon or pure aluminium. The wafers are introduced by a cassette system. In the case of this tool, they're put onto a platen here inside the chamber, the vacuum chamber. You can see the 3-pin positions, which are the lift pins to lift the wafers up when they're finished to come out. But basically, once they're all loaded, this machine will then strike an argon plasma, and the argon ions have sufficient energy with the DC bias in the tool that they will sputter off aluminium, and the aluminium will coat the surface of the wafer. And here we have another important tool. This is a Novellus PECVD tool. This tool deposits low temperature oxide and oxynitride and silicon nitride, depending on the process requirements. It's needed as a low temperature passivation layer typically, or an intermediate passivation layer. But basically, the purpose of the low temperature is to ensure that we don't move the diffusion profiles around in the silicon. And here we have the finished processed wafers. Good. Here we are in an annex clean room for Fab 1. So this is the actual sputterer that deposits the alloy, special alloy. This tool has been consigned to us by the customer, and it illustrates a business model Semefab is pleased and glad to adopt, where if a customer requires a special process and they want to consign a tool to us, we will make a place for it and run a special process for it. Here we are in Fab 2. This is the MEMS fab. This is where we make sensor products. This fab is completely separate from Fabs 3 and Fab 1, and in fact there is only one-way traffic allowed from Fab 1 and 3 into here. Nothing can go back the way. And the reason for this is that we process in here and use materials which are incompatible with the processing in Fabs 1 and 3. Things like gold, platinum, heavy metals, and potassium hydroxide are all very, very harmful to the active integrated circuits that we make in Fab 1 and 3. So this is the central corridor. This is the area. This is built on a slightly different principle. We have the various bays going off here for photo and for thin film, etching, metallization, diffusion. So it's a microcosm or miniature form of Fab 3. Once wafers are in here, we have to be able to complete them. So we've got a suite of operations in here which parallel what we have in Fab 3. This is a 6-inch and 4-inch compatible fab, so we can handle both side diameters of wafers. So here we are in the photo area for Fab 2. As I was saying, it's a smaller version of Fab 3. We've got the same kind of tools here for coating and for developing. We have ASML stepper for doing the fine line width lithography. And down at the far end, the guys are working on a contact proximity stepper, which is used for certain of the steps, and which also has double-sided aligning capability. This tool is a wafer bonder. Sometimes in MEMS processing you want to take two substrates and actually stick them together, maybe with a cavity between or something like that. So that's what this tool is capable of. It's a eutectic and anodic bonder. So we're in the plasma etch bay here. A variety of tools to cater for 4-inch and 6-inch wafers. Let's go down and see. So here we have 4-inch lamb tools for poly, nitride and oxide etching. Here we have the 6-inch equivalents. These are very minimalist from inside the clean room. There's a whole load of stuff on the other side in the service chases. This tool is our second STS Pegasus tool for deep reactive ion etching. This is a 4-inch and 6-inch compatible tool as well, and we use it to get that very vertical etch step in the silicon instead of the bevel. Finally, we have a surf scan tool here and an optical profiler for doing the dimensional measurement and also for measuring particulate levels on the wafers. So this is the sputter bay in Fab 2. We have two MRC sputters. Each sputter contains 4 target positions, and we can have different materials on those targets. So we can do things like titanium, nickel, silver, or titanium, chrome, gold, different combinations. Some metals need an adhesion layer underneath of them to stick well to things like silicon nitride surfaces. This tool in particular is actually configured with two very precious metals, gold and platinum, which are used very much in medical situations because they're inert. So medical sensors, which are going to be in contact with bodily fluids such as blood or urine or something like that, they need to have this type of processing to give the sensor good longevity in the application. Here we have a machine called a deck tack. This machine is basically a step height measuring tool. So once we've deposited metal, maybe we've lifted off a pattern, we can check on here to see what the thickness of the metal is that's been left behind. So just to explain, lift-off is a technique where we put the photoresist down first and then we put the metal on top. And we're able to create a re-entrant profile in the photoresist like a cliff overhang, a bit like a cornice on a mountaintop. And when we put the metal down, it's discontinuous along the surface because it's shadowed essentially. And if you have the photoresist down first and it's profiled in that way, you can put the wafers into acetone and you can actually dissolve away the resist and you lift off the metal at that point, leaving the pattern behind. So it's a technique that's very useful for these hard to etch metals. Things like gold and platinum are quite inert and they don't etch very well. We're now in a metrology and PVD bay. We carry out various functions in here. One such function is to use micromanipulators if we need to probe into the surface of the chip at any point to measure electrical characteristics. Another tool that we have is the scan electron microscope. And this tool is used when we need to see three-dimensionally what's happening on the surface of the chip. Sometimes you can get a pattern, something like a metal pattern that looks perfect, but actually it's discontinuous on the step. But when you're looking down like that, you don't see anything. You need to get in to see it on the side, and then you can see if it's got a crack in it or not. So that's really where the SEM comes into its own. And this tool has an analytical tool on it. It's called EDX, and it allows us to target any part of the chip, and we can measure the elemental composition. So if there's a defect on the chip, and we think, where did that come from? We can analyze it with this, and we can get a clue as to where it came from. And actually, this system, made by Oxford Instruments, carries a silicon chip as part of its circuitry in there, which is actually made in this wafer fab. It's quite a nice story. And then we have two other tools here. These are PECVD again, another PECVD system for the same function as we had in Fab 3. Is to put down those low temperature dielectrics needed for the passivation and the intermediate insulator or dielectric. Now, one of the reasons why we're expanding Fab 2, this fab, is because this wall really cannot be used for equipment, and it ought to be able to be used. So by pushing out the boundary wall of this building, we're going to create two new chases with their service chases behind. So we will finish up actually with an ability to have 3 extra walls of equipment the full length of this clean room. And we already have customers lined up for some of that space. One customer is a manufacturer or developer rather of millimeter scale batteries. These are chip scale batteries that can be used in the body to monitor pressure, for example, in the heart and send signals back, but equally can be used in Internet of Things applications using energy harvesting as the medium to recharge these millimeter scale batteries. So this is the etch bay, and where we do what we call liftoff, which I've explained earlier. This is the solvent bench and the liftoff bench where these processes are carried out. We have to be very careful of fire hazard with things like acetone, so that every bench like this has got a CO2 suppression system fitted to it. In this section of the etch area, we have what we call KOH etching, potassium hydroxide etching. And this is carried out in this bench here. The potassium hydroxide is heated. I think it's heated to about 60 degrees. And we have our DI water tubs and our quenching and so on in here as well. As I was saying earlier, this process leads to a bevel on the etch. As you go through the silicon, you finish up with a 52-degree angle, and as a result you're wasting space on the surface of the wafer. If you can etch vertically, you get rid of that, and you get much greater number of die on a wafer. In fact, you can go from 5,000 to something like 12,500 die by avoiding this process and using the DPRIE system. And finally, in Fab 2, we have our diffusion capability here. It's a single quad stack furnace. It does give us the ability to do anneals, metal alloys. Metals like platinum need to be alloyed at a certain temperature for a certain time in order to stabilize everything and to produce a constant resistance. Quite often platinum is used as a temperature sensor, and it needs to be stable with time. So this is the purpose of these furnaces. In the bottom tube here we have an LPCVD system, which is the low pressure vacuum pump on the furnace. It enables us to deposit polysilicon or silicon nitride or even silicon dioxide, depending on the configuration at the back. We can clean wafers in here, various functions that can be carried out. And very often with MEMS, it's a case of relatively low volume but good pricing. So we need a versatile and flexible wafer fabs situation to be able to process those products, and this is what this and the other systems that you've seen here today enable us to do. Thank you. We're about to go into Fab 3 to review all of the processes and the tool sets that we have in there. But it's just worth mentioning this little preprocessing unit here is actually a portable clean room itself. For reasons of efficiency and also for quality, we've consolidated all of our photo operations in Fab 3. So all of the Fab 1 photo, for example, comes into Fab 3 to be carried out. So we are mixing 4-inch and 6-inch wafers in the Fab 3 photo area. And they're transported in this little miniature clean room between the two fabs, so we maintain the sort of integrity of the air quality inside there, exactly the same as the clean room. And there's a docking port here and docking ports in Fab 1 to enable the wafers to be transferred without any contamination. So now we're going into Fab 3. This is our newest clean room. It's a Class 10 facility in photo. Air handling goes through the floor, and it's a state-of-the-art facility for the type of technologies that we're running. Okay, well here we are, suited, booted and goggled, and we're ready to go into Fab 3. The first area we're going to see is the photo area. The first thing to notice in the photo area is the yellow light. This is because we're going to coat the wafers in here with a photosensitive layer, which is then going to be subsequently etched in one of the other bays that I'll show you shortly. The design of the Fab 3 cleanroom is different to Fab 1 and Fab 2 in that we have ceiling to floor airflow from the HEPA filters in the ceiling down through the floor, and then any particulate that's in the environment is swept away back into the air handling system in the plant area, where any residual particulate can be filtered out. Essentially you've got a continuous polishing process going on of the air, both in photo and in all the bays that we're going to see shortly. The first step in photo is an HMDS bake. This is a vapor of hexamethyl disilazane, and it's an adhesion promoter. It creates a good surface for the resist to adhere to so that it doesn't get washed off during the etching process. After the HMDS step, we're now going to coat the wafers. We have several coaters here with different photoresists set up on them. But basically, the wafers are going to have resist spun onto the surface of the wafer. It's going to spin off to create a very uniform thin film. At the end of the spin cycle, the wafer will lift and it will come to the exit cassette. This intermediate step is actually what we call a pre-bake. It's on a hot chuck, and that drives some of the solvents out initially before the aligning process takes place. You notice that these are 6-inch wafers in process here. A 6-inch wafer has got more than double the area of a 4-inch wafer. So for the same unit of work that we put into the wafer, we get twice as many die as a result. And there's the wafer coming off to the exit cassette. So in this area here, we're going to align a pattern to the wafer. It's very important as we build up the layers that we get accurate registration of each pattern. So we have to have a system of automatic alignment and checking to make sure we get accurate registration. Here we have the photomasks that are used for projection aligning and also the master reticles for the stepper, which I'll show you shortly. In projection alignment, the entire image on the mask is transferred to the wafer in one scan of ultraviolet radiation. And you'll see that shortly as we set up a wafer for you to see as it goes through the Perkinelmer. So here's an example of a master mask. It's got all the pattern information on it for a given device. You can see that there's a very thin film on top of the pattern. It's spaced off by a few millimeters. It's called a pellicle, and that protects the optical integrity of the image on the photomask. What we're doing here is examining the pattern on the wafer and the pattern on the mask. The technologist operating the machine can see both images, and they make sure they're in perfect alignment before pressing the expose button. When the expose button is pressed, ultraviolet light shines down through the mask and polymerizes the photoresist. Essentially, it transfers a pattern from the mask onto the wafer. And this is it starting the scan now to transfer the image completely from the mask to the wafer. So here we have the developer system that needs to take place after the alignment process. The wafers come onto the center position where they get sprayed with a variety of developers. The exposed resist washes away and the existing resist that wasn't exposed remains, and thus we create a pattern. The wafers come off onto this cassette where they're ready for a subsequent bake to harden the resist, and then we're ready to go after the QA process step. We're ready to go into the etching or implantation steps. Here we have our ASML stepper. The stepper is a different methodology from the Perkinelmer scanner in that it steps the image across the wafer rather than transferring the image in one complete scan. That enables this machine to have better resolution than the Perkinelmers. This machine can print down to 0.7 microns, whereas the Perkinelmers are limited to 2 microns. Just to put this in perspective, a human hair is 0.04 of an inch in thickness, or roughly 100 microns. So if you take a human hair and split it 100 times, that is the size of the features that we are able to print with this machine. Semefab makes a very broad range of semiconductor devices, from discrete semiconductors, 3-terminal devices, diodes, transistors, through integrated circuits, CMOS, precision analog, and sensors. When I say sensors, I'm talking about pressure sensing, gas flow, blood viscosity, and other types of esoteric sensors. One of the features of sensors is that it's sometimes necessary to have patterns on both sides of the wafer. Sometimes we need to etch the back of the wafer to create a thin membrane structure on the surface of the wafer. So where we need to do double-sided alignment, we start off the process with double-sided wafers, and we coat at very different stages in the process. We'll be doing patterning on the back. And this is our double-sided aligner here that allows us to do that. So the camera systems on here image both the top and the bottom of the wafer so that we can bring them into alignment, and we can expose the back of the wafer in order to create a pattern. Good job, perfect job. Process control is a very important part of what we do at Semefab. For every single operation, we have a quality control gate. In the case of photo, we're looking at the integrity of the film, the uniformity of the pattern on the wafer, and we're measuring a critical dimension to make sure that when we etch the wafer, it's got the right size of features for the device operation. So here we are in the PVD bay, where we do sputtering and we do the deposition of dielectrics such as nitride, oxide, oxynitride. We have two sputter systems. This one is for aluminium silicon, aluminium copper, and the adjacent system here, sputter 7, does the same processing. So here we are in the ion implant bay. What is ion implantation? Well, it's a technique for actually taking charged particles of either boron, phosphorus or arsenic and accelerating them through a vacuum, what we call beamline, and raster scanning them, just like the old black and white TVs, raster scanning them across the surface of the wafer to create a uniform dose across the wafer. And we have two machines that perform these processes. One is a medium current machine, one is a high current machine. Let's go and look at them. So here we have the Varian 350D medium current implanter. This machine is configured for 6-inch wafers. It has a dose capability up to about 1E15 maximum, and it's used here for things like VT adjust implants at the 10 to the 11 dose level, P-well implant 10 to the 13, 10 to the 14 level, and occasionally at the 10 to the 15 level. But frankly, this is not the tool to do really heavy ion implants. We need something with a bit more beef behind it, and that is the tool here, the 180XP. This machine is capable of accelerating the charged particles with 180,000 volts. I think that 350D is good at 120, so this is a more powerful machine in that sense. It's also capable of dosing up to the level of 5E16 or even higher if you have the time for the implant. And it's got two end stations, so we can cater here for 4-inch and 6-inch wafers. As we go to the next bay, I'm going to show you the etching bay. But this is an example here of what we call a service chase. So in a service chase, the nuts and bolts of the equipment are available to the equipment engineering team to carry out routine maintenance. Sometimes it's something as simple as an oil change on a pump. Sometimes it's a more complex operation, a target change on a piece of equipment or something. So here we are in the plasma etching and the wet etching bay. We have a variety of plasma etch tools here. We've got the LAM 9600, this one's for metal. We've got the 4520, that's for oxide and nitride, and then the 4420 at the end, that's for polysilicon. So all of the major material layer depositions are etched with these tools. Over here we've more plasma processing. We've got the TGAL 915, that's a plasma resist strip process, and we've got a TGAL 901 here, which is used for oxide and nitride etching. Here we have the conventional wet chemistry etching. We have the ability to put different etchants in temperature controlled tubs, and then in front of them we've got the weirs, the rinsing weirs with 18 megohm centimeter water running through them. So we're able to etch, rinse, and then we put them through the spinner to create the final clean and etched product. It's necessary after certain steps to measure feature sizes outside of the photo area, for example after etching. And some of these feature sizes are so small that it's difficult to measure with the type of technique that we had in Fab 1, and you saw also in photo the nanoline. So the CD SEM gives us an ability to measure really small features. SEM stands for scan electron micrograph. So this is actually using electrons rather than photons to image the line width that we're looking at. And here we have a Novellus PECVD system. This is similar to the system that we had in Fab 1. This is the low temperature deposition of oxide, nitride, oxynitride that we need to have after we've put our diffusions, our implants, etc. into the wafer. Once we've set those up with the high temperature diffusion profiles, we don't want to disturb what we call that particular SRP, spreading resistance profile of the impurities diffused into the silicon. So any subsequent processes where we need a dielectric layer have to be done at lower temperature, and the plasma addition to the process here gives us the ability to take the temperature down to of the order of 700 degrees, which is below the temperature at which we're going to get any significant movement in the impurity profiles. So here's an example of another service bay in Fab 3, and you can see the considerable space that's taken up actually by some of these tools outside of the clean room. Fab 3's plant room. On the gantry above we've got the full air handling system for the entire wafer fab. Down on the ground floor we've got the deionized water plant and compressed air and some other facilities. This is a reverse osmosis plant for purifying the water as it comes in from the town mains. So here we are in the diffusion area. This is where we're doing high temperature furnace processing. We're oxidizing the wafers, we're depositing boron or phosphorus, we're driving in these impurities into the surface to an accurate level, and we're driving in the ion implantation doses. And in some cases we're also doing what we call LPCVD, which is relatively low temperature chemi-vapor deposition of materials like polysilicon and silicon nitride. Here we have a tool called an FSI Mercury. You saw the pre-diffusion clean system in Fab 1, which was pretty similar to the etching bays that we've just seen. In other words, bulk acids were being used to clean the wafers. Here we're using a spray tool. This machine is kitted out with delivery of HF, hydrogen chloride, ammonia, and sulfuric acid and peroxide, hydrogen peroxide. So all these quite aggressive materials come in here as part of a programmed cleaning cycle to make sure the wafers are at their absolute best for going into diffusion and high temperature processing. Okay, so when we come to the end of the process, the wafers need to be evaluated electrically and visually. In this area we do the electrical evaluation. There are two stages to this. There is the evaluation of the wafer for its basic fundamental process characteristics. These are simple devices, resistors, diodes, simple transistors, continuity structures and so on. Which tell us that the process has been done okay. And once, we call that wafer map. Once the wafers have been through wafer map, they are allowed then to move on to the probe test proper, which is a functional probe step. Let's go in and we'll see it in action. Okay. One of the features of the probe and test clean room is actually that the floor is anti-static, and that means that any static charge that you build up as you're walking around is dissipated through the floor. And actually people that are working in here, when they come in, they have to use a foot ground and a wrist strap, and they test themselves on here to make sure that they've discharged any static electricity on their body. The reason for that is that static, if it's imparted to a wafer, can either kill a wafer or it can create what we call a walking wounded device. And if it escapes into the field, it could subsequently fail. This is an example of a probe test card. If you come and take a good close look at it, you'll see that there's an array of needles here that come to a point which is on the same surface or planar surface as the wafer will be. And these are slotted into the testers, and the chuck moves underneath, and each die position is presented to these needles for the electrical test to be carried out. So there are two functions carried out in the probe and test area. The first one is to measure what we call the wafer map characteristics of the device. We have some special structures on each wafer, regardless of the design, on any given process, that tell us if the process has been done correctly. So these are, if you like, you could think of them as primitive designs of fundamental devices like resistors, diodes, transistors, which tell us, and continuity structures, for example, that check the contacts are being made and that they are ohmic contacts. So if you look at a wafer such as this, you can see that there are, if you get the light in the right angle, you can see that there are north, south, east and west and centre. You can see these marks, and those are the marks with the fundamental test devices on for what we call wafer map, and they will be tested first to prove that the wafer is good. If they pass, the wafer then goes on to 100% probe test, and that means that every die on this wafer will be electrically tested with a different probe card on a different probe setup. If the die, this looks like quite a small die on here, is 1 by 1 millimeter, there will be 15,000 candidates on a wafer. 15,000 candidates will take something like maybe 2 or 3 hours to test, depending on the test time. So in this area we are functionally probing wafers. In other words, we're testing 100% of die on each wafer. And this system here is actually running now. So underneath the probe card here, the stage is moving progressively. You can see how quick it's testing. It's going through at a fair rate, and each die is being tested. This number here is 7,750 roughly, if I'm reading right. And every time that number goes up, it's another good die on that wafer. The total number tested here is 9,200. 7,800 are good, and it gives you some feel of the electrical yield that we're getting on this particular wafer. If we take the example of the 15,000 die wafer, then we will probably yield about 12,500 die on that wafer. And 12,500 die would actually sell in the market, depending on the function, anything from a couple of cents, maybe up as high as 15 cents. So if you just pick a standard figure of, let's say, 5 cents a die, 12,500 die, one wafer will be valued at $600. And in one of these boxes here, we have 24 wafers. So 24 wafers at $600 is something about $1,400. Sorry, $14,000 for those 24 wafers. So that gives you an idea of the value that we have built into the product when it comes through to this stage. A box of wafers can be anything from maybe $5,000 right up to $20,000, $30,000 depending on the product. Finally, in here we're doing what we call final testing. For some of our customers, we send the product abroad for assembly into packages. So these, if you look very closely, you'll see that this is full of tiny little black packages. And that's the form of a normal integrated circuit that you know as a silicon chip. You normally see them in this form. So these have been assembled onto a header, bonded, and then encapsulated with plastic, and then put into those tubes. And we bring them back here, and we put them through these test handlers for final testing. So again, every device is tested individually for final test. These can test at extremes of temperature as well. We can test at -40 and +120. And if the chip is going into a critical application, like an automotive application, we do indeed test at the extremes of temperature to make sure the chip is going to be functional in all weather conditions that a car might be exposed to. Here you can see the die building up in different channels according to the pass test criteria. So these are the pass channels here. When we complete our wafers, our customers expect them not only to perform electrically, but to be perfect visually. So this is our QA final inspection area, where we inspect the wafers according to the customer's agreed criteria. Semefab's future plans entail an expansion of Fab 2 to give us some two extra bays, and also demolition of Fab 1 and replacement of Fab 1 with an 8-inch facility. And where we're standing here will be approximately the front of the 8-inch facility, covering all of the area of Fab 1, and this area at the back of us, this grey box will be disappeared, and it will come out roughly to this sort of a line, with a second floor on top for office accommodation.